Hello viewer, and welcome to the summary of a computational map of the proof CO molecule adsorption and dissociation on transition metal low Miller indices surfaces. My name is David and I will be your guide through this little trip. Let's start talking about the interaction of the CO molecule with transition metal surfaces. This interaction is widely studied since it appears in a lot of different catalytic processes. Furthermore, this interaction also helps to obtain atomistic information of the surface thanks to the properties of the CO molecule. It's because of this importance that this paper aims to find trends and descriptors for the adsorption and dissociation of the CO molecule on these different transition metal surfaces and to find which of them can have the best activity as a catalyst in different processes. This paper has aimed to study 27 transition metals. These have been classified depending on its crystalline structure. We have in green BCC transition metals, in blue HCP transition metals, and in red FCC transition metals. And depending on its crystalline structure, the three most stable surfaces have been defined. However, on each of these transition metal surfaces, the CO molecule will be adsorbed. This molecule has three different possible conformations. One is parallel to the surface and the other two are perpendicular, connected to the carbon or the oxygen respectively. We also have to study the co-adsorption of the carbon and oxygen atoms, since this is the product of the dissociation of the CO molecule. All of these have been adsorbed in the highly symmetrical sides of each of the surfaces, which are the ones shown on screen. But please refer to the supplementary material to have information and the entire list of the adsorption sampling. With all of these, we can go to the results. Let's start talking about trends and descriptors. For the four different properties that have been calculated, being them the CO adsorption energy, the carbon and oxygen co-adsorption energy, the carbon monoxide dissociation energy, and the carbon and monoxide dissociation activation energy, trends have been found, but most importantly, the demand center has been found to be a good descriptor for the four of them when we compare all the data together, but better when we separate each of the transition metal surfaces depending on the crystalline structure. Now, if we look into the specific data, we can find three different situations. First, early transition metals have been found to absorb the CO molecule very strongly and to be able to dissociate it with a very exothermic reaction and low activation barrier. On the other hand, we have the complete opposite with late transition metals that interact weakly with the CO molecule and the dissociation reaction is very endothermic with high activation barriers. Finally, we have a third situation, which is a middle point between both of them, with middle transition metals that have activation and adsorption energy with middle values between both of those characteristics for early and late transition metals, and reaction energies that are more isothermic. Now we can look into a comparison between both the reactivation energy and the reaction energy. This can be done with the BEP relationship, which helps us to find which is the best catalyst for different situations. In case we want a catalyst for the breakage of the CO, we can go to middle transition metals and we can specify the rhenium 11-20 as the best one. On the other hand, if we do not want to break the CO molecule, late transition metals do the trick, specifically those FCC transition metals, that with their high activation barriers, they permit to keep the integrity of the CO molecule. Finally, we would like to thank all the associations that helped in the making of this paper and you for getting at the end of this video. Thank you very much. All the links for this paper will be found in the description, and don't forget to leave a like, subscribe in case you want more videos like this, and we will see you very soon. Goodbye!